Hi everybody, my name is Chloé Guennou. I'm a PhD student here at the Institut d'Astrophysique Spatiale. So I'm going to present very quickly my work, from which the main question is, can the differential emission measure constrain the timescale of the energy deposition in the solar corona? Thank you. So just a quick reminder about the DEM, because I'm not sure that all people here is familiar with this concept. So the DEM provides information about thermal structure of the coronal plasma. Indeed, we can express in case of optically seen plasma, as this is the case for the solar corona, the intensities can be expressed as this expression. So this is in fact the integral of the product of two functions. The first function is called the temperature response function and takes into account all the physical processes at the origin of the coronal emission. And the second function is called the DEM function. The DEM provides the amount of emitting material present along the line of sight as a function of the temperature. So now how these formalisms can help us to constrain the frequency of the heating. So in case of active regions, the observed DEM often follow a power law, as we have an example here coming from this paper. We have the DEM here as a function of the temperature, and we can observe here a slope. So determining this slope can provide indication of the cold to warm material ratio, and this is an important quantity to characterize the nature of the heating. For example, if we consider a very long time between two different heating events, the plasma has time to cool, and thus we have the contribution of cold material here in the DEM, and thus the DEM will be smoother. But in the other case, if the time between two different heating events is very short, the plasma doesn't have time to cool, and thus the contribution coming from the low temperature will be less important, and then the slope here will be steeper. So this is an important parameter to determine. But there is some complication when we want to infer the DEM, because if we want to infer the DEM, this means to inverse this integral. And there is some complication because this is an inverse problem, and this is a nil-pose inverse problem. The presence of both random and systematic error complicates the determination of these quantities. So the question in this work is, what is the confidence level of the reconstructed slope? Because this is an important parameter to determine. So we developed a technique to study these parameters. This is a technique only based on simulations and using a Monte Carlo treatment of the different uncertainty sources. So we used 30 different lines observed by the eye spectrometers coming from 6 different elements and covering a large range of temperature. Then we adopt a model for the active region DEM, defined by 2 parameters here. We have the slope alpha and the temperature of the peak TP here. Then we compute both simulated observation and theoretical intensities, and we include measurement noise and also the systematic errors. And then we use a simple least square inversion to determine the DEM. All the different uncertainty sources lead to 25–30% of total uncertainties. So with this technique, we can compute all the solutions consistent with a set of data and their associated probabilities, and from this we can derive confidence level on the estimated DEM slopes. So just one example of our results. So here we have a probability map for the slope. So this is the probability that the plasma has a given slope, knowing the results of the inversion. We have here the true plasma slope and the measured slope for a given set of observations. The diagonal here corresponds to an agreement between the both, and we can observe here a spreading of the solution around this diagonal, especially for the high value of the slope. So now let us imagine we took a real set of data of ice, and we measure a slope of 5. With this kind of plot, we can obtain the probability distribution of all slopes consistent with the data. Well, here we have the probability distribution of the solution, and from this probability distribution, we can compute the standard deviation, giving indication on the confidence level of the reconstructed slope. So doing this, we can obtain the mean value and the confidence level on the slopes measured. So just a short application of our results. So here in this table, there is this is the slopes coming from all these papers, measured for 22 different active region cores. And Bradshaw et al. Wanted to compare if these results in the literature compare these results to their model. So their model of low-frequency nanoflares predict a slope between 0.8 and 2.5. So for now, we have 36% of slopes consistent with their model. But now, if we include the uncertainties derived in this work, estimated here about 1, we have in the more optimistic case, 77% of slopes consistent with their data. But on the contrary, in the less optimistic case, 0% of the slopes are consistent with their model. So we can conclude from this that it is difficult to strongly constrain the timescale of heating event given the different uncertainties involved in the problem. Thank you.